Hello, everybody. I'm Babak. Thanks for the introduction. And I'm going to be talking about our work on deobfuscation. So this was a joint work with Brian Johannes Meyer, Ben Whiteley, and Shamir Debray, all from the University of Arizona. So first of all, what is deobfuscation? We are referring to deobfuscation as opposed to obfuscation as a transformation or process that, given a given an obfuscated program, it will produce a simpler program that is simpler to understand and easier to analyze. And the thing is that this process should not be change the functionality of the code or the program that was obfuscated. So the reason or the motivation for this for having such a deobfuscation process is that a lot of malicious codes use obfuscation techniques, all sorts of various types of obfuscation techniques to protect their code from being analyzed or being reverse engineered. For example, as it is shown on this slide, the program on the right, the CFG is shown here, is the binary search program, which was obfuscated using Themida, which is a commercial obfuscation tool. So as it is obvious from the slide or the CFG, the program on the right, which is obfuscated, is much, much more complicated to analyze, well, manually, and it is, of course, subject to errors. So our goal is to have a technique or tool that automatically, given an obfuscated program, can identify and extract all the significant operations or the logic that was embedded in the obfuscated program and produce a simpler program, which, as you see in this case, well, our tool, namely, was able to recover the original logic of the program, which was binary search. And the thing is that the recovered logic might not be exactly the same as the original program, but it is a lot simpler and easier to understand and analyze, and it has the semantics of the original program. So there have been a few related works to deobfuscation. I have some of the most relevant here. So Kugan uses equational reasoning and assembly level instructions to identify relevant instructions to the original code and to simplify deobfuscations. The problem with this approach is that it is hard to extract higher level information like CFG or syntax trees from the simplified trace. Sheriff also uses abstract variable binding to reverse engineer the emulator that was being used to obfuscate. But the again, problem here is that they are making strong assumptions about the underlying obfuscation being used. So for example, if the emulator is being used to unpack the logic of the binary, I mean, the unpacker routine has been emulated, then this approach will not give us what we are looking for. So our main contribution here is that we are not making any assumption about the underlying obfuscation that is being used. So in order to start the deobfuscation process, we need to define what is significant about the program that we want the deobfuscation process to preserve. So we are defining a program as a mapping from its inputs to the outputs. So then our deobfuscation, we want a deobfuscation to identify this mapping, the computation that involves this mapping from inputs to outputs, extract this information from the obfuscated program, and somehow simplify this. So this is our system overview. We first get an execution trace of the program using an emulator, which in our case is Ether on top of Zen. And then we do identify inputs and outputs to the program. We propagate taint from inputs and from outputs backward to identify all the computations that affecting or are affected by the input and output values. Then we find control dependencies, and then we apply some simplification transformations on the code. And then from the simplified trace, we construct a final control flow graph. We have also added a concurrent execution engine to our system, so it can be fed either from the original trace, obfuscated trace, or the simplified trace, and it can build path constraints in the trace and suggest other inputs to the user that could cause the program to execute other execution paths. But I'm not going to be discussing about this part in this talk. So first, let's discuss the taint analysis. I'm just going to go over an example to see how these analyses are used in our approach. So first, as I said, taint analysis. So here you see the code for a simple factorial program. It reads n from input and computes the factorial in a loop and finally prints the results. And here on the right, we have the execution trace of the program for n being 3. So the loop actually is being executed twice. So the first step is to finding inputs and outputs to the program. The sets of breathe here is an input to the program. So we first identify these and propagate taint forward from this input. So this identifies the 3 if statements in the program as being forward tainted. Then we do a backward taint on outputs of the program. So we start propagating taint backward from the values that flow into output functions, which is right in this example. So well, this will identify instructions that affect the values going to output functions. Well, the next step after doing taint analysis is to find control dependencies. And here, the purpose of the control dependencies is that we find all those instructions that are affecting the output, but are potentially subject to simplification. So, but the thing is, they are being controlled by some input values. So, for example, here, the multiplication of fact is dependent. The number of times that this multiply is being executed is dependent on some input value. So, for simplification, we don't want to simplify this part of the code. So we find these control dependencies, and well, the code that I showed you here is not an obfuscated one, but finding the control dependencies in obfuscated code might be challenging, especially in obfuscations like CFG, flattening, or emulations, where you don't have the control dependencies that are present in the original program. So we have a notion of implicit control dependencies. So these are those control dependencies that are due, that are caused by some data dependencies. So we, for finding implicit control dependencies, we first identify explicit control dependencies using post-nominator relationships on CFGs. Then we find implicit data dependencies, which is similar to implicit tainted values. And then we consider all the control transfers that are based on some implicit tainted value. So we actually treat those control transfers as like the conditional jumps. So then after finding the control dependencies, so we have actually identified significant instructions or statements in the trace that we want to keep. Then we apply some simplification transformations. And these transformations are basically semantic preserving, meaning that they don't change the behavior of the code or like a basic block. They are generally compiler optimizations such as constant propagation, dead code elimination, and copy propagation, and etc. And the thing is that these transformations need to be controlled. As I said, we need to keep the things that are significant in the program. So we need to be careful that we don't simplify those computations away. Then we have the simplified trace. we need to build a control flow graph out of the simplified trace. But the problem here is that for some obfuscations, for example here, emulation, the issue is that emulator uses the same piece of code for different for the same functionality for every instances of that functionality in the original program. Let's say a branch, a conditional branch used like multiple times in the original program. They all being transformed to one piece of code in the obfuscated code, probably with different inputs or arguments. So what we end up having in the simplified trace or the CFG, if we build the CFG normally from the simplified trace, we often see basic blocks that have multiple successors and multiple predecessors for one basic block, which doesn't make sense. So what we do, we try to duplicate these basic blocks as a way of distinguishing different instances of using one functionality in the original code. So, so this actually reduces the number of spurious paths in the final CFG. So for example, if the combination of predecessor 0, basic block B, S0 only happens in the trace, we don't need to have a basic block that has all the combination of these three predecessors with basic block B and all the successors following that basic block. So we basically limit the number of possible execution paths in the final CFG. And before actually showing some numbers for evaluation, I'm going to show some CFG examples for like two programs. So this is binary search program on the left, the original, that's the CFG for the original program. And in the middle, we see the obfuscated program. And the picture on the right shows the CFG we were able to recover from that obfuscated trace. And this is for Fibonacci program, we used drop gadgets to build the Fibonacci program. And as you see, our tool was able to recover the original logic of the program from the obfuscated trace. And we have also measured the CFG similarity of a bunch of programs. For emulation-based obfuscation, we used 4 commercial obfuscation tools: Code Virtualizer, Executor, VM Protect, and Themida. And so the red bars show the CFG similarity of the obfuscated programs to the original programs. And the blue bars show the CFG similarity of the simplified programs, again, to the original programs. And we did the same thing for ROP programs. So we used 4 ROP programs. And we built these ROP programs ourselves. We didn't actually do malicious ROPs because they were like so trivial and easy. So these programs that we've selected have interesting structures. So as you see, the average CFG similarity is generally above 80% with regards to the obfuscated code. So in conclusion, we've described a generic approach to deobfuscation, and well, as I said, we make no assumptions about the obfuscation being used in the code. We consider programs as a mapping from its input to its output, so that's the only assumptions we make about the programs. And so this deobfuscation approach identifies and simplifies the computation that involves in this mapping from the input to output. And our evaluation shows that this approach was successful against both emulation and ROP obfuscations. So I guess that was all. If there's any question.
So we have time for a couple questions. So Juan Caballero from India Software Institute. So why is the CFG similarity the right metric here for evaluating your deobfuscation? It seems like if what you want is like a deobfuscated program with the same semantics, you should run deobfuscated code and actually have the same, observe the same semantics or behavior that you would actually have with deobfuscated code.
So, well, ideally, yeah, that's the case, but we were not able to actually run the simplified code because of like some memory issues, like pointers and those stuff. So that's our goal actually, but we're working on it, but we haven't got there yet to be able to execute the simplified code.
Okay, thank you.
Saman Zanus, Rutgers University. Great piece of work. If I understand correctly, you're using concurrent execution to make sure that all the code is exercised. And I was wondering if a packer could not possibly just put a lot of branches to just make this concurrent execution kind of visible.
So packer can do what? I'm sorry?
So basically, the obfuscator puts a lot of branches so that concurrent execution in reasonable time cannot cover all the code.
So that's actually, well, interesting. So this is what happens with, we have examined some other tools like S2E and, well, some other tools. So the thing is that for our purposes, taint analysis should be precise to identify only tainted or input dependent conditional branches. So this is what causing other tools to fail on obfuscated codes. They are not able to precisely find only tainted conditional branches. But we have some refined taint analysis that only identifies tainted conditional branches.
Thanks.
Can you do a double translation and come up with a grammar for obfuscation, given an obfuscated piece of code?
Double transformation?
Yeah. Also, what happens if you run it on ordinary code?
Basically, it's like similar to the compiler optimization. So it doesn't change the code much because there's nothing to simplify.
And what if the obfuscator changes the semantics of, so, I mean, there are ways to carry out factoring through set operations.
Well, they don't basically change the semantics. One obfuscator might change some instruction or operands to one instruction in the original program, but they don't change the semantic in any ways.
What if they did?
Well, then, well, what we produce from the unobfuscated program has this new semantics added to the original program.
Hey, hello. Hey, this is Fish from UC Santa Barbara, and this is a very interesting piece of work, and I think it's very astonishing. I have two questions about it. The first thing is that I think deobfuscation is not, I mean, it's really about to make this program simpler, but it's really not only about simplifying the CFG, right? So for example, like there's a paper in 2008, it talks about how to make opaque conditions. For example, like you can encode your conditional operations or your conditions basically in a lot of like mathematical expressions. And I think it's super hard to actually reverse it. And it's definitely not something that you can reverse it just by data flow tracking or data dependency tracking. How are you going to handle it? Or are you handling it or not? And the other thing is about
Can you limit to one question, please?
Sorry?
So, can you just limit to the first question?
Okay, sure.
So I guess again, that depends on how precise your taint analysis is to identify the tainted conditional branches, right? So for example, in executable, we find a lot of conditional branches. Some of them are introduced by the obfuscator, and I mean, some of them are tainted actually, but they don't change the behavior of the code, so we cannot simplify those. But a lot of the others that are not dependent input, we can't simply get rid of those because no matter what the input is, the result, we know the result of that conditional jump.
Do you think this is really generic?
I don't see why not.
Awesome, thanks.